Hello everyone. In this series, I will talk about gamma function and beta function. So gamma function, I will take for gamma function I will take maybe two classes, and for beta function I will take one or two classes. Okay. Let me write down what are the references I will follow. The reference one will be references. So reference one will be special functions for scientists and engineers by W. Bell. And reference 2 is mathematical methods in physical science by Marie L. Boas. So these are the two references I will mainly follow. So let me start with something we already know, that is factorials. The factorial function. So let's assume n, which is any natural number. Any natural number. That means n will be 0. N will take values like 0, 1, 2, 3, 4, and so on. So we know that n factorial is defined like 1 times 2 times 3 times dot 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 times n minus 1 times n up to n. Okay, so this is how n factorial is defined, and it can also be written as like so if I follow this definition, then this is n minus 1 factorial. So it can also be written as like n times n minus 1 factorial. So it's kind of a recursion relation. Okay, so if I know n minus 1 factorial, then how can I calculate n factorial? So I need to multiply it by n. So these kind of relations are called recurrence relations. So these n are taking natural numbers. So now I will define this factorial function. I will define these factorials in a different way. Let me start with something kind of abstract. So let me start with an integration, that is e to the power 0 to integration 0 to infinity e to the power minus alpha x e to the power minus alpha x dx, where alpha greater than 0. And if I do this integration, let me call it I, or let me call it let's say I0. And if I do this integration, if I calculate the integration, then it will be I can write it like limit, this is infinity. Okay, so limit let's say k tends to infinity, integration 0 to infinity, 0 to k, 0 to k e to the power minus alpha x dx, right? And if I do this integration, then it is limit k tends to infinity, it will be e to the power minus alpha x divided by minus alpha, right? And lower limit will be 0, upper limit will be k. So now which is basically, I can take this minus 1 by alpha outside. So then it is limit k tends to infinity e to the power minus alpha k minus e to the power 0, and which is nothing but minus 1 by alpha limit k tends to infinity e to the power, so e to the power minus alpha k, and alpha greater than 0, so it means I can write it as e to the power alpha k minus e to the power 0 is 1. And what is this value? So if alpha greater than 0, so if alpha greater than 0, so in that case, for k going to infinity, this value will be 0. This value will be going towards 0. So the limit is basically 0 if alpha greater than 0. So we are left with then 1 by alpha. So what we got is basically I0 equals to integration 0 to infinity e to the power minus alpha x dx equals to 1 by alpha. Now if I differentiate it with respect to alpha, so what we will get, alpha can also be a variable. While integrating with respect to x, I am treating alpha as a constant, but alpha can also be a variable which is independent of x. So I can treat alpha and x, both are two independent variables. So in that case, I can differentiate with respect to alpha. So it will be a partial differentiation. Like I do del alpha 0 to infinity to the power minus alpha x dx equals to, in the right hand side, I can write del alpha of 1 by alpha, but here it's only a function of alpha. So there is no need of writing a partial derivative. I can also write dd alpha. Both will be correct. Then if I do this partial derivative, so here the integration is with respect to x, and I am doing the derivative with respect to alpha. So in that case, I can take this derivative inside, and if I do the derivative of e to the power minus alpha x with respect to alpha, then what I will get is nothing but minus alpha, which I can write outside of the integral 0 to infinity. Sorry. So if I do del alpha of e to the power minus alpha x dx equals to, so if I do this integration, it is minus 1 by alpha square, and if I do this differentiation, then it is minus x times e to the power minus alpha x. So what we are left with is minus, okay, so this minus sign, so here in the left hand side there is a minus sign, here there is a minus sign, and here also there is a minus sign, so they will cancel. So I will omit this minus sign, and we are left with integration from 0 to infinity x e to the power minus alpha x dx equals to 1 by alpha square. So let me call this equation 1, let me call this equation 1, let me call this equation 2, and this let me call I1, let me call it equation 2. Okay. Similarly, if I differentiate it again with respect to alpha, I will get I2 equals to 0 to infinity. You can do it as a homework. It is x square to the power minus alpha x dx equals to 1 by alpha cube times 2. Let me write it equation 3. Similarly, if I differentiate it again with respect to alpha, then I will get I3 equals to 0 to infinity x cube to the power minus alpha x dx equals to 3 times 2 divided by alpha to the power 4 Okay, let me call it equation 4. And here I can write as, instead of 2, I can write it as 2 times 1. So that means I can write it as 2 factorial. Instead of 3 times 2, I can write it as 3 factorial. Right? Here instead of 1, I can write it as 1 factorial. And here instead of 1, I can write as 0 factorial. Because I know that 0 factorial equals to 1. Right? So provided 0 factorial equals to 1. And if we follow this trend now, if we follow this pattern, I can write that 0 to infinity, I can write as in equals to 0 to infinity x to the power n e to the power minus alpha x dx equals to n factorial divided by alpha to the power n plus 1. And here alpha I am treating as a variable, so I can put the value of alpha as 1. So if I put alpha equals to 1 in this equation, then we will get 0 to infinity x to the power n e to the power minus x dx equals to n factorial. If I put alpha equals to 1, then this term will be 1, and here alpha times x will be only x. Right? Or instead I can write it as n factorial equals to integration from 0 to infinity x to the power n e to the power minus x. This is called the factorial function. So n factorial can also be written like this. This is called the factorial function. You can check, you following this factorial function, that 0 factorial will be 1. So that's, you can take as a homework. Now look carefully. Here what I did is basically I have showed this factorial function, which is n factorial. Here n, throughout this proof, while deriving this pattern and all, this n, it will take values, so from 0 and then 1, 2, 3, right? So this n is basically a non-negative integer. So factorials are defined like, for example, n factorial, the n should be a non-negative integer. That's what we have learned in our 10 plus 2 mathematics. Now the question is, what about functions? Sorry, what about fractions? So for fractions, a special special kind of function is defined, that is called the gamma function. Okay, and gamma function, it will incorporate integers as well as fractions. So the question is basically, what about non-integral values? So the answer is gamma function. Gamma function. And it is defined as gamma of some p, where this p is basically some number. Okay, for example, treat it as a number p, which is So here p is greater than 0. And how it is defined? This gamma p, where p is greater than 0, it is defined as integration from 0 to infinity x to the power p minus 1 e to the power minus x dx, p greater than 0. So this is how the gamma function is defined. It's a new function and this is how it is defined. Now let's say n is an integer value. So for example, let's say n is a positive integer. In that case, gamma n, it will be 0 to infinity x to the power n minus 1. If I follow this definition, e to the power minus x dx. And if I follow this definition of factorial function, it is basically n minus 1 factorial. See, here there is n minus 1. And here for n, it is n factorial. That's how the factorial function is defined. Now instead of n, we have n minus 1. So here I can write it as n minus 1 factorial. So for integer value, for if n is a positive integer, in that case gamma n is same as n minus 1 factorial. So this is how these gamma functions are related to the factorials. Similarly, gamma n plus 1, which will be 0 to infinity x to the power n plus 1 minus 1, that is nothing but n, e to the power minus x dx, which equals to n factorial. So for example, then gamma 1 will be 1 minus 1 factorial, which is nothing but 0 factorial, which equals to 1. Gamma 2, which is 1 factorial, equals to 1. Gamma 3 equals to 2 factorial, equals to 2. Gamma 4 equals to 3 factorial, equals to 6, and so on. So this is basically the gamma function for integral values, positive integral values of n, and these are directly related to these factorials. For positive integral values of n, gamma function is directly related to the factorials. So now what happens if we have some non-integral values? For example, gamma of, let's say, p plus 1, okay, and I want to know how it is related to gamma p, how it is related to the gamma p. So n I am reserving for integral values and p I am reserving for, I mean, p is a common parameter. It can take integral values also, it can take non-integral values also, but p should be greater than 0. So it can take any positive value, any positive real value. So for p greater than 0, let me start with gamma of p plus 1. Following this definition of this gamma function, which is gamma p equals to integration from 0 to infinity x to the power p minus 1, right? So here instead of p I have p plus 1. So I will write integration from 0 to infinity x to the power p plus 1 minus 1, and which is nothing but x to the power p, times e to the power minus x dx. This is how the gamma function is defined. This is the definition. Now you might think that by using the factorial function, this is nothing but p factorial. But wait, p is not necessary to be an integral. Okay, p can be function, p can be fractions also. So in that case, I cannot write it like this. I cannot write it in terms of factorial functions. What I need to do is I need to do integration by parts. So I can treat this x to the power p as the first function, and then this is the second function. And what I will do is basically integration by parts, which is I can write this x to the power p as it is, and I will do the integration of e to the power minus x dx, okay, minus I will differentiate with respect to x this first function, that is x to the power p, okay, and then times the integration of e to the power minus x dx, okay, and I will integrate this whole thing with respect to dx from 0 to infinity, and here also the limit will be from 0 to infinity. Now let's look at this integral. It is nothing but e to the power minus x with a minus sign. So if I put the limits, then it is x to the power p with a minus sign, e to the power minus x. Let me put this minus sign outside. So e to the power minus x, and limit x tends to infinity, sorry, e to the power x, limit x tends to infinity minus 0, right? If I put this 0, so then because this factor present here, it will be 0. And this integral, so here it will be, if I differentiate this first term, this term, then it is p times x to the power p minus 1, and what about this term? It is nothing but minus e to the power minus x. So in that case, this integral I can write as, so here there is a minus sign and here there is another minus sign, so that means it will be plus integration from 0 to infinity. I can put this p outside this integral, so p and e to the power p minus 1, x to the power p minus 1, e to the power minus x dx. Now let's look at this limit. What can you say about this limit? Here you can see this x to the power p, if I take x tends to infinity, then this also tends towards infinity, and e to the power x, this also tends towards infinity. So then how do we calculate this limit? So it's basically infinity by infinity force. Okay, there are lots of ways, there are lots of different ways to to tell what will be the value of this limit is. One very easy way to tell is like e to the power x. If I expand this e to the power x, there will be, in the expansion term, there will be all different powers of x present. So like it will be 1 plus x plus x square divided by 2 factorial plus x cube divided by 3 factorial plus dot dot dot, all x. So in this expansion term, x has all powers. So there will be powers higher than p for some particular value of p. For example, there will be some there will be lots of terms, infinite number of terms where x is a power of, where x is a power which is greater than p. So in that case, this denominator, it will go towards infinity much faster than this x to the power p. So the idea is, and following this idea, it also follows that let's say if you have a polynomial means that sum over an x to the power n, and this n is going from, let's say, 0 to some finite number. Okay, this capital N is finite, it's a finite number, it's not infinite. So in that case, if when x goes towards infinity, then this polynomial will also goes towards infinity, and also e to the power x will go towards infinity, but e to the power x will go towards infinity much faster than this polynomial. It's because here in the expansion of e to the power x, there are all kinds of powers of x are present. There will be infinite number of terms present for which x has a power which is greater, which is higher than this capital N. That's one way. Another way to calculate is, so I mean that way basically says that okay, e to the power x will go towards infinity much faster. So in that case, x to the power p divided by e to the power x will go towards 0, right? That's one way. Another way, just use L'Hospital's rule, and if you differentiate it, p times basically, then it will be a constant. So x to the power p if you have, and if you differentiate it p times, then it will be a constant. And if you differentiate it how many times you want, it will remain the same. And after that, if you put the limit, then in the denominator it will go towards infinity, and you will the whole term will go towards 0 basically. Okay, so my point is e to the power x always go towards infinity much faster than in any other polynomial or any other x to the power p. In that case, as a x tends to infinity, this function, okay, this limit will be 0. So in that case, what we are left with is gamma p plus 1 equals to only the second term, which is p times 0 to infinity x to the power p minus 1 e to the power minus x dx. Now if you look at this term, what is this? This is nothing but this gamma p, just the definition, right? So this whole integral is nothing but gamma p. So what we are left with is gamma p plus 1 equals to p times gamma p, where p can take any positive value, any positive real value. Okay, so this is a recurrence relation. This is a recurrence relation for gamma function. It basically says, what do we mean by recurrence relation? Recurrence relation basically says that if I know, if we are given this gamma function at some value of p, and we are asked to find out the value of this gamma function at some other values, which is p plus 1, then how can we find it? So how this gamma p is related to its next value, that is gamma p plus 1. And this relation will tells us, the recurrence relation will tells us. So whenever you will learn about this Legendre function, Bessel functions and all, then you will we will talk about this kind of recurrence relations. Okay, it's a very important recurrence relation. And now let me show some problems. So problem one, which is basically the application of this recurrence relation. So problem 1 is, show that gamma 1 by 4 divided by gamma 9 by 4 equals to 16 by 5. How do we show? So here you can see gamma 9 by 4, right? And if I am using this formula like gamma p plus 1 equals to p times gamma p, equals to p times gamma p, So then it will be easier to, you know, to first calculate, uh, to first put this gamma 9 by 4 through this recurrence relation, and let's see what happens. So if I start from gamma 9 by 4, I can write it as gamma 4 plus 5 by 4. 9 I can write as 4 plus 5, which is nothing but gamma of 5 by 4 plus 1, right? 4 by 4 is 1. And following this recurrence relation, I can write it as, this is P basically now. This is P. So it is gamma P plus 1, which equals to P, that is 5 by 4, times gamma P, that is again 5 by 4. Simple. I am just using this recurrence relation. Again, I will write this 5 by 4, and instead of gamma 5 by 4, I will write it as 1 by 4 plus 1. And then if I follow this recurrence relation, so now this is P, it will be P, that is 1 by 4 times gamma P, that is 1 by 4. It is 5 by 16 times gamma 1 by 4. So what we got is gamma 9 by 4 equals to 5 by 16 times gamma 1 by 4. Then if I take this to the right hand side and if I take this to the left hand side, then what we are left with is gamma 1 by 4 divided by gamma 9 by 4 equals to 16 by 5, and this is what we are asked to show. This is one application of gamma, this recurrence relation. Let's solve another problem. Express as a gamma function. Okay, and the integral is basically 0 to 1 ln 1 by x to the power whole to the power p minus 1 dx. So we are asked to express this whole integral in terms of gamma function. What we will do is, I will take x equals to e to the power minus u. It's because I have ln of 1 by x. In that case, 1 by x is e to the power u, and ln 1 by x is u. So instead of starting from here, I can also start from here. So I can take this whole term as u. Same thing. And dx is minus e to the power minus u times du. And so what I will do is I will basically replace this x by this u. In that case, I also need to replace this limit. So for this limit, if you can see that as x equals to 0, if x equals to 0, in that case it implies, so if I put here, so here if I put x equals to 0, in that case this 1 by x will tend towards infinity. And if I write, let's say this is ln y, this is y, so then as this ln y function, it looks like this. So as y goes towards infinity, then ln y will also go towards infinity. So in that case, when x goes towards 0, 1 by x goes towards infinity, and this ln of 1 by x, it also goes towards infinity. So it means the u, it will go towards infinity as x goes towards 0. So that means u will tends to infinity. And if as x tends to 0, and if x equals to 1, if x equals to 1, so if I put x equals to 1, so then it is ln of 1, and what is ln of 1? Ln of 1 is 0. So then u equals to 0. And now let me write down this integral again. So integration from 0 to 1 ln 1 by x whole to the power p minus 1 dx equals to, so now I will replace this x by u. So in that case, the integration limit, that will also be in terms of u. So instead of x equals to 0, I will write infinity. For x equals to 0, u tends to infinity. That means infinity. And for x equals to 1, u will be 0. It is 0. And instead of ln 1 by x, I will write u. So it is u to the power p minus 1. And instead of this dx, I will write this term, which is minus e to the power minus u du. And now I can put this minus outside this integration, so it will be minus infinity to 0 u to the power p minus 1 e to the power minus u du. And as there is a minus sign, I can just interchange this limit. So it's basically I can absorb this minus sign and write it as integration from 0 to infinity instead of from infinity to 0. Why is that? The answer is very simple, because after the integration, what you will do is, let's say you have an integration from, let's say, a to b and some fx dx. So after the integration, what you will do, you will just do the integration, and let's say you got some function gx, and you will put the limit, which is from a to b, and that is nothing but minus g of b minus g of a, and which is nothing but g of a minus g of b, and which is basically from b to a fx dx. So that is when a is the upper limit and b is the lower limit. So if there is a minus sign basically in front of a integration, instead of in front of a definite integration, so in that case it will just interchange. If I absorb this minus sign, it will just interchange the upper limit and lower limit. So here that's what we will do. So I have already done that, and the rest of the terms will be as it is du. And this is nothing but, if I follow the definition of this gamma function, this is nothing but gamma of p. So instead of x, we have u. So this is nothing but gamma of p. So what we have proved is basically 0 to 1, integration from 0 to 1 ln of 1 by x whole to the power p minus 1 dx equals to gamma of p. So this is another form of this gamma function. Okay. So maybe in some applications you will see that the limit, the limit, integration limit will be from 0 to 1. So instead of from 0 to infinity, instead of going from 0 to infinity, so here this gamma function is defined like the limit, integration limit is going from 0 to infinity. So now in some cases where there will be where you will find that the limit is from 0 to 1. So in that case, you can define this gamma function like this. So it's a new way of defining a gamma function. Okay, but the limit is from 0 to 1, not 0 to infinity. Now let's do another problem. Express as gamma function, and the function is, the given function is 0 to infinity x to the power minus 1 by 3 e to the power minus 8x dx. So what do we do? Let me write down the gamma function again, the definition of gamma function, which is 0 to infinity x to the power p minus 1 e to the power minus x dx. So here, instead of e to the power minus x, we have e to the power minus 8x. What I will do is, I will treat this 8x, in this integral, I will treat this 8x as, let's say, y. In that case, x equals to y by 8, also x to the power 1 by 3 equals to y to the power 1 by 3 divided by 8 to the power 1 by 3, which is nothing but 2. Also x to the power minus 1 by 3 equals to 2 times y to the power minus 1 by 3, and 8 dx equals to dy, or dx equals to dy by 8, and the limit will be the same, because if I put x equals to 0, then y will be 0, and if I take x tends to infinity, then y will also tends to infinity. So the limit will be same. So then this integration, the given function, that is 0 to infinity x to the power minus 1 by 3 e to the power minus 8x dx. Now if I replace this x by y, then we are left with integration from 0 to infinity x to the power minus 1 by 3, I can write as 2 times y to the power minus 1 by 3 instead of e to the power minus 8x, so I can write as e to the power minus y. Okay, e to the power minus y, and instead of dx, I will write as dy by 8. So this 2 and 8, if I cancel, then I will get 4. So I can write this 1 by 4 outside the integration, and then it will be integration from 0 to infinity. And this 1 by 3, now I will try to put this whole integration in terms of this this gamma function, so that is x to the power p minus 1. So here we have y, instead of x the variable is y, so this y to the power minus 1 by 3, this I can write as 2 by 3 minus 1, and it will be e to the power minus y dy. Now if you can recognize, this is the definition of gamma function for gamma 2 by 3. So if this 2 by 3 I can consider as p, so this will be gamma p, following the definition of gamma function. So what we got is basically the value of this given integral, which is 0 to infinity x to the power minus 1 by 3 to the power minus 8x dx equals to 1 by 4 gamma 2 by 3. This is the solution. So these kind of problems are very important for gamma functions. So in the description I will put some assignments, you can practice if you want, and in the next class I will talk a few different properties of this gamma function, and then I will move towards the beta function. So that's all for today. Bye.